Now we will work on homogeneous linear systems with constant coefficients. Well, sometimes in differential equations, we are asked to solve a system of differential equations. And when we want to solve these systems, we get three different cases when either we have distinct real roots for eigenvalues, equal real roots, or complex roots. And since in this course we are focusing on 2 by 2 matrices, our cases will be distinct or complex. And depending on those cases, we will have several formulas to solve these differential equation systems. Well, for distinct real roots, which we will be covering today, we will have x of t equal to c1 e to the lambda 1 t v1, where v1 is the eigenvector, plus c2 e to the lambda 2 t v2, where v2 is the second eigenvector, and lambda 2 and lambda 1 are the second and first eigenvalues respectively. And this should look similar because in distinct real roots we did have the same format of the solution, just that our solution was we didn't have any vectors in it. Well, in this case, since we're working on systems, we will have vectors. Also, it is important to note that in some questions we will be asked to find the constant coefficients such as C1 and C2, and using initial conditions will help us solve these problems using IVP problems. When we plug those values in, we will be able to determine what the constant coefficients are. And for the next lecture, what we'll be covering is we will work on complex roots. And for complex roots, we'll have two complex eigenvalues, and our eigenvalues will be like a plus or minus bi, where a is the real part of the eigenvalue and b is the non-real imaginary part of the eigenvalue, and our solutions will be something like this as below. And in this lecture we're not going to work on those a lot. We will be focusing on those in the future. Now let's solve this linear system. We are given that x prime equals to a matrix times x, and we are given an initial condition, and we are asked to find what x of t is. Okay, what is x of t? So since this is a differential equation system, the best approach is to start with solving for the eigenvalues. Well, our matrix will be what is giving us the eigenvalues, so I'm just going to go ahead and write the matrix. Our matrix A, I can call it matrix A, you can call it whatever you want. It's going to be this matrix 5, negative 1, 3, 1. And let's start with trying to find the eigenvalue. So what we did last lecture was we were subtracting lambda I from the matrix A to get the eigenvalue. So I will do that, and we will have a matrix looking like this. I subtracted lambda I from the matrix, so on a diagonal we will have negative lambda. And now we want to find the determinant and set that equal to 0 to find the lambda. We want to solve for the lambda using the determinant. So we're going to have 5 minus lambda multiplied with 1 minus lambda minus 3, okay, because it's 3 times negative 1 is minus 3, so we're gonna have minus 3, and this is the determinant of matrix A, and we are going to set this equal to 0, so we're gonna be able to find what lambda is. So I'm just gonna distribute this multiplication, 5 negative lambda, and we're gonna have a negative lambda from there, so we're gonna have negative 6 lambda plus lambda squared plus 3 equals to 0. Therefore, we're going to have lambda squared minus 6 lambda plus 8 equals to 0. Now, you can notice that this we can factor this out as lambda minus 2 and lambda plus 4. So let's go ahead and do that. So we're going to have lambda minus 2 and lambda plus 4. If you're not sure, just distribute this in your head. Try to do like the small distribution. Lambda squared, negative 4 lambda, minus 2 lambda, negative 6 lambda, negative 2 times negative 4 is negative plus 8. So this is the correct distribution. we're going to set this equal to 0. Therefore, our lambdas will be lambda 1 equals to 2 and lambda 2 equals to 4. Nice. Now we know that we have two distinct real eigenvalues. Two distinct real eigenvalues where we're going to use this formula right ahead, what we just covered for distinct real eigenvalues. So we're going to go ahead and put this over here, and let's go ahead and generate our solutions. So we are also required to know what v1 and v2 is, and they are obviously the eigenvectors. So before we jump into the solution, we need to build the eigenvectors. So we're going to go and plug the eigenvalues back into this system phi minus lambda matrix. So we're going to be able to solve for the eigenvectors. So let's start with lambda 1 equals to 2. Okay, so for lambda 1 equals to 2, we're going to have this matrix phi minus 2. Okay, 5 minus 2, negative 1, 3, and 1 minus minus 2. Okay, actually no, 5, 1 minus 2, just minus 2, guys. Okay, and we can go ahead and write this more clearly, and we got literally the same equations on both rows, and now that we have this, we can pick either one of the equations. I'm gonna pick, like, it's pretty much the same thing, so you can pick any one. Even if we had different numbers, we could have a 6 and a negative 2 on the bottom row, but that wouldn't change anything because the equations are the same equations. So this will be x1 and this will be x2, so we're gonna have 3x1 let's say minus x2 equals to 0. Okay, so 3x1 equals to x2. So we were able to solve x1, x2 in terms of x1. So our free variable is x1. So x1 multiplied with this vector will be 1 and 3. So this means our eigenvector v1 is going to be this vector. And let's do for the other eigenvector as well. So other eigenvector was lambda 2 equals to 4. So I'm going to have 5 minus 4. Let me check that out. Negative 1, 3, and 1 minus 4. Okay, this is for lambda 2 equals to 4. I'm just going to make a small division here so it doesn't get confused. And we will have this 1, negative 1, 3 and negative 3, and these are also the same equation, so you could still go ahead and pick any one of those equations to find the eigenvector. So we're going to have x1 minus x2 equals to 0, so x1 is equal to x2. When we have this, we are able to say we can define any one of those as a free variable. Okay, I'm going to define x1, and x1 is a free variable, and x2 in terms of x1 is just x1 because it's the same thing. So our eigenvector vector 2 will be 1, 1. Now that we have our eigenvectors, I'm just going to go ahead and write those real quick. Eigenvector 1 was 1, 3, and eigenvector 2 was 1, 1. Okay, and our eigenvalues are 2 and 4. So now we can build this system, and we are able to solve this differential equation. Well, x of t is going to be c1 e to the lambda 1. Lambda 1 is 2 t v1. Okay, 1, 3 plus c2 e to the 4t and 1, 1. Okay, but guys, don't stop here. This is not your entire solution because this is an initial value problem. Okay, we are not, if we didn't have the initial condition, yeah, but we have an initial condition, so we're gonna go ahead and plug that initial condition to solve for c1 and c2. Okay, x0 equals to, I believe it was 2, negative 1. Okay, so we're gonna have 2 and negative 1 here. So we need to get this matrix, this vector. Every vector is also a matrix, so this matrix when we substitute 0 for t. Okay, so I'm gonna first build this in a matrix form so we can work on easier, more easily. So just distribute these constants into the vector and add these guys together. So for the first vector, we're gonna have c1 e to the 2t multiplied with 1, and 3 times c1e to the 2t, and this is our first vector, and we're going to add this vector to both of the constants are 1, so we're gonna say times 1 c2 e to the 4t times 1. Okay, and let's just add those together. So this is still a 2 by 1 matrix. This is still a vector. Don't try to add a new column here. This is not a new column. This is just adding to one entry. We're just making a matrix addition here. So we're going to have c1 e to the 2t plus c2 e to the 4t. And on the bottom row, we're going to have 3c1 e to the 2t plus c2 e to the 4t. Now, I know it looks complicated and it looks scary, but it's totally okay because we're just going to go ahead and plug the initial value. That's pretty much it. So just plug x0 into it. So x0, okay, equals 2 and negative 1. We know this information. And now we're going to go and plug 0 into t. So c1 and e to the 0 is 0, so we can just leave it. E to the 0 is 1, I'm sorry. And c2 e to the c2 times e to the 0, so we're going to have c2 here. So we know that c1 plus c2 is going to be equal to 2. Now we're going to get the second equation on the bottom, and we're going to be able to solve for c1 and c2. That's really amazing, isn't it? I think it's really amazing. So we're gonna have 3c1 e to the 0, so just that's just gonna be 1 plus c2. Okay, and now we have a beautiful equation. We know that c1 plus c2 equals to 2, and 3c1 plus c2 equals to negative 1. Well, there are many ways you could solve these systems of equations. What I like to do is just eliminate one term by adding or subtracting, and now we can subtract this equation from the top one, so we can basically get another equation. So c1 minus 3c1 and c2 minus c2 is 0 equals to 2 minus minus 1. So we're going to have 3. So we know that negative 2c1 equals to 3, so c1 equals to negative 3 over 2. Once you solve one of the variables, the other one comes out from any equation. I'm going to go ahead and plug it to the first equation. So c2 will be 2 minus c1, and c1 was negative 3 over 2, so we're going to have minus negative 3 over 2. So we're going to have, for, I believe, 7 over 2. 7 over 2 will be c2. Is that right? Yeah, 7 over 2. So we are able to find our constants now. We have our constants. So we're gonna go ahead and plug that into x of t function. So our x of t function was like this. We converted that to a matrix. You can leave it in the matrix and that would also work. You can also leave it in constant coefficient form. That's also totally okay. So I'm gonna go ahead and plug these coefficients into this matrix system. Okay, so C1 was equal to negative 3 over 2. So we're gonna have negative 3 over 2 e to the 2t plus C2 was 7 over 2. 7 over 2 e to the 4t. And 3c1, so c1 was negative 3 over 2, so we're gonna have negative 9 over 2 e to the 2t. E to the 2t. I want to make it look better. 2t. Plus c2 was 7 over 2, so we're going to have 7 over 2 e to the 4t. And basically, this is the solution for this differential equation system over here.